Hello, I'm Daniel, and I'm here to present a tracer that just joined in the kernel, which is the OSNoise tracer that helps you to figure out who is stealing your CPU time. And so I'm a principal engineer at Red Hat. I'm a kernel developer, and I have interest on real-time and runtime verification. And I'm here to talk some results that arrived in the kernel from research. I'm a postdoctoral researcher at Scuola Superiore Sant'Anna in Italy, and away from keyboard, I do photography for mental health and cycling for body health. So I'm a regular user. How can I see who is stealing my CPU time? You stop, bim bam boom, you're done. Questions? Well, but there are still some slides for the non-regular users, right? So just a quick introduction. What is OS noise? The operating system noise is a well-defined high-performance computing metric, and it's basically the interference that is experienced by an application because of operating system activities. And it's generally a fine-grained metric. So the main interest on this kind of metric is the result on the delays in the final of the computation, because generally HPC workloads work in parallel. You have a dispatcher that dispatches the many jobs in parallel, and then it waits for all the jobs to get done. But because of operating system noise, some threads can be delayed more than the other, creating a sort of vacuum and throwing away some of your precious CPU time. And that gets even worse when you have a multiple CPU time, right? And HPC is also often connected to the low latency environments, right? Because low latency communications nowadays are enabling sub-milliseconds applications in the cloud or real-time applications in the cloud, and are enabling services that rely on it. And many of these options are being actually possible because of 5G. And 5G uses massively the network function virtualizations that actually run on Linux, right? So in this sense, the OS noise is bad because it accumulates over the hops on the internet, increasing the delay. So trying to find a way to figure out who is stealing your CPU time is getting more and more important, and the granularity is getting finer and finer. So a little bit of the state of art. Nowadays, the operating system noise is measured using user space tools. They basically loop reading the timer or reading the time system counter, and they try to detect when there is a delta time between two consecutive reads that are higher than a threshold, right? And then they get these values higher than the threshold. They call this jitter or latency. And once you get a bad value on a platform, you need to stop doing the things, stop doing the benchmarking part, and then start to do some kind of debugging tracing, trying to figure out from where these bad values came from. And it usually requires a lot of human interpretation of the trace, and I spent a lot of time myself doing this kind of job. And well, it's not that practical, right? And that's the main, trying to analyze this problem that I was having. The main part of this problem comes because the trace and the benchmark tool are not synchronized. So, and this leaves some gaps for interpretations and doubts, because you don't know if the latency that you saw or a noise that you saw on a previous section where you are just doing the benchmark are the same cause for the one that you are doing the debug, for example. And there are too much room for speculations. You know, what can cause noise? Was it a thread, IRQs? And also, there is no clear definition of this metric when you think on the Linux or real-time Linux community. And other than the operating system, we have the noise induced by the virtual machine, if we're running on a virtual machine, or by the hardware. And for these, nowadays, we need to use yet another tool, which is, for example, a hardware loud detector. And you know, it works. We can use them. They are useful, but it can be better. So how can we make it better? Uh, the first thing that we need to try to achieve is trying to figure out a tool that can inform you from where this noise came from. And for this, it's important to make both the workload and the tracing of that benchmark section run synchronized in synchronism. And try also to automate the tracing, right? Trying to make the trace as much human readable as possible, right? Giving you precise information. And based on this kind of problems and this kind of needs, I came up with the OSNoise tracer. So the OSNoise tracer, it's a kernel tracer based on the ftrace infrastructure that dispatches both the workload that will measure the OS noise and the tracing that enables the understanding of the causes. So the workload and the trace, they are synchronized in kernel. And likewise, other tools, the OS noise, it loops reading the time and trying to figure out when we have like a delta time that's higher than a threshold. That you see, okay, uh, some other entity stole my CPU time, and boom, this is a noise. But but it not only measures this time that was stolen, it also accounts the interference that came from the operating system. And that's a precious information when debugging the problem, as you see later when trying to use the tracer. So how can I enable the tracer? As I said, it's in kernel and it's based on ftrace, using ftrace infrastructure. So you use it inside the tracing directory in the kernel. Just join the trace directory, set OSNoise as your current tracer, and read the trace output. So by reading the trace output, you will see a vision like this. And this is the trace output. So the trace output is emitted per CPU on a period, and this period is by default 1 second. And that's the runtime in microseconds that you can see here. It's 1 second in time. And while reading the timer in this entire 1 second, the tool noticed that the operating system stole 190 microseconds of the CPU time, giving us a net runtime for the tool of 99.98100 percentage of CPU available. And also in all these consecutive reads, the higher noise detected on a single noise, it was 9 microseconds, which is very impressive, right? And after these timing outputs, the tool shows some counters saying from where this noise came from. It could be from hardware, NMI, and IRQ, and you'll see more about these later. So, as I said before, there are some configurations. For example, the period that the tool will run before emitting these partial reports is the period in seconds. We can set the runtime, and we can set other configurations that will allow you to stop tracing and fine-tuning the threshold that detects you the occurrence of a noise and so on. But we will need more time to explain this. Just let's keep moving. So, okay, in that report, I can see how much CPU time my HPC workload can have and how much noise is creating from CPU time. But I still didn't say how can I find the sources of the noise, which is the main advantage of this tool. So before mentioning who is stealing my CPU time, I need to understand what can cause OS noise on the operating system. So On Linux, all the task abstractions can steal time from a workload. And on Linux, we have basically NMIs, IRQs, softirqs, and threads that can preempt your HPC workload. But outside of Linux, we can also have like SMIs from the processor stealing you time. And if you're running on a virtual machine, you can also have the host preempting the virtual machine, and this can be nodes on the application running inside the virtual machine, right? And so to be able to observe who is stealing your CPU time, some trace points were added to the kernel. And these trace points, they tell you which task context preempted your busy loop thread or your HPC workload, right? And these trace points are the NMI noise, IRQ noise, and softirq noise, and thread noise, right? These are basically the kind of tasks that can preempt your busy loop thread. And there is yet another trace point, which is once these two consecutive reads of the time detects that there was a gap higher than the threshold, it prints you, okay, I've noticed this huge gap, and this gap was this amount of time, and it was interfered by this amount of time. And you can see here in this example better why this is important, right? So I enabled my tracer in the second line. I enabled all the OSNoise events, and then my tracer will dispatch a busy loop thread on all the CPUs, keep running and reading the time over and over again, right? And I've set here in the fourth line saying, okay, tracer, stop the tracer when I hit a noise that is higher than 8 microseconds, right? I want to have less than 8 microseconds, so I set the tracer to stop because I want to figure out who is causing this 8 microseconds noise, right? I let it run until the tracer stopped, and here we have one example of this output. So as you can see here, there is the workload running on CPU 7. It received a timer that took almost 2 microseconds. Then in CPU 8, the timer was also fired, and it also ran for 1 microsecond. And later, we had another timer occurrence in the CPU 8, and this time it took longer, it took 2.8 microseconds. And right after, we can see that there was a thread that was scheduled on the same CPU, and it was the migration thread. That ran for 3 microseconds. And so far, the tracer didn't detect, right, a noise until the point where a simple threshold trace point is fired. And this simple threshold was fired right after the thread noise, right? You can see the timestamp is the same, and it says that at the starting time, it notes that something preempted this thread for a longer period. This longer period was 80 microseconds, 8 microseconds, right? So it's not always clear when it started, right? One could get this start time and try to read backwards the trace, comparing the timestamp, but that's annoying, and that can take you a lot of time. But because the tracer runs in kernel and it can synchronize the tracing and the workload, the trace took note that from the last time it read the timer until the second time it read, right? The gap was 8 microseconds, and it also accounted for 2 interference. So I can just look back for the two last occurrence of noise on that CPU, and then you can figure out which workload or which kind of task abstraction is stolen the time. And here you can see that it was this this timer on the third line of the trace, plus this noise from the migration thread. So it was likely the the migration thread that was awakened by the timer that caused this noise that I was looking for. And then I can go deeper in tracer, trying to figure out why this migration thread was being fired on my isolated CPU, right? And this can have other causes like other threads, and then you can start this as a starting point for your deeper debugging session. So how about the operating system noise, right? Uh, the SOS noise tracks all the source of the, I'm sorry, and how about the hardware noise? So SOS noise tracks all the sources of the operating system noise. When interference happens without any evidence of a thread or IRQ or NMI running, we can infer that the cause was the hardware when we see the counter of interference as 0, right? And the cause of noise can be from outside of the OS. And the good thing about this is that I can use this tool like I'm used to use hardware lat detector, but I can do this in parallel, not running first hardware lat detector and then like sysjitter to detect the occurrence of hardware noise. And that's a good advantage. You can save a lot of time on the debugging session, right? And the hardware lat detector or this gap can be either from a physical, like SMI calls, or a virtual machine. So here we have an example of the trace output, and it's pointing me on the interference counter that yes, there are some hardware interference coming from the hardware. So if your system is on a bare metal and it's tuned for low latency, there should be no hardware latencies here. And if you see these numbers, you can likely start debugging the BIOS of your system and so on. On the other hand, if it is a virtual machine, it will be natural to see these numbers. But as long as they don't keep pushing your maximum noise or the amount of noise at a value higher, you can tolerate, right? So for example, here in the first line, you're seeing you're seeing hardware latency happening, but as the maximum noise is just 9 microseconds, it can be tolerable, for example. That's a very good number, actually. But as you can see in the third line, it can be higher. So yeah, you see, at least from here you know to where to start and look at, and just not getting a number. So here's an example of the trace output where the occurrence of the noise is from the hardware. As you can see, you're also seeing on the fourth line, you're seeing that you have an 8 microseconds threshold, a noise, and the interference is 0. So this is clear that noise from the hardware. So as final thoughts, the OSNoise tracer puts the workload and the tracer in a single tool. It provides you information and tracing that can point you to the root cause of the root cause of the noise, and it reduces also the overhead of the data that you are putting to the trace output because it's processing in kernel. It's giving you only the information that are really useful, and this also helps reduce the overhead of the tool. It can be used to detect the hardware latency. In the same session where you are trying to find OS noise, you can find hardware noise. In addition to the OS noise, there's a sibling tracer that is the timer lat that gives you all the tracing output for the noise, all those OS noise trace points, but to the timer latency, similar to the cyclic test. And well, these tracers are new. They just landed in the kernel, but they are being currently enabled on Fedora and future versions of CentOS and Red Hat. And soon you hear about the RTLA tool, which is a user space tool that enables and collects this tracer information to the user space and give you more facility to use now this infrastructure. And that's it. Thank you.